Hey, thanks everyone. It is a pleasure to be here virtually. Of course, I would much prefer to be there in person with everyone else. Of course, since I'm off in the States right now, I'll have to ask you to please reach out if you'd like to discuss any of this material later. I'm more than happy to set up a Zoom call or email with folks if they're interested in this work or have further ideas. I did get to visit the Isaac Newton Institute a little bit earlier in the session, and it was delightful. I cannot believe that they managed to put a university in the middle of a cow pasture, and it's really nice. So thank you to the Newton Institute folks. Thank you to the organizers of this session. And today I am happy to tell you about a project on Motivic Hochschild homology. Here you can see that I'm going to reference the classical Hochschild homology, topological, and then motivic. If anyone has any idea what kind of graphic you can use to evoke motivic, email me your graphic because I'm stumped, but A1 will have to do for now. Let's get started with an outline. So I know that some folks in the audience do have expertise and prior knowledge of Hochschild homology. Nonetheless, there might be some folks who don't, and I will spend some time reviewing the basics and then building up to both topological and motivic variants of that theory. That'll be kind of the review portion. And then in part 3, we will jump into the new content, which is a computation of the Motivic Hochschild homology of FP, the field with P elements, over an algebraically closed field. So I wrote spec C here, but here C could have characteristic L. And then I want to conclude with some further directions that I hope this research indicates. And who knows, maybe one of you before the day is over will have an answer for me, or maybe it's something we can talk about more in the future. This is all based off of a preprint that's on the archive right now called Hochschild homology of mod P motivic cohomology over algebraically closed fields. And this is joint work with my collaborators, Bjorn Dundas, Mike Hill, and Paul Arne O. So if there are no questions, I'll get started. I can probably keep an eye on the chat as we go here. I don't know if there's a way for folks in the audience to jump in verbally, but feel welcome to.
So Kyle, can you hear me now?
Much better, yes.
Okay, so we've got a microphone and they'll be able to ask questions. We'll got it working.
Okay, great.
Go ahead, go ahead.
And please do, yes. All right, so all right, let's review the classical theory for a bit. So what is Hochschild homology? Our setup here is in just the most basic terms. We're going to work over a field K, and we'll have a commutative K algebra A. And then we can build this extremely concrete Hochschild complex. So we'll have the n-fold tensor power of A there, and then the differential. I've written down the formula here, and you're welcome to stare at it, but it's perhaps easiest to see when you look at, say, a tensor 3 mapping to a tensor 2. I've written that here, and the simple tensor ABC goes to AB tensor C minus A tensor BC plus CA tensor B. So in that last one, you see the C hopping over to the front, and there's something kind of circular there. So we'll come back to that. The definition then of Hochschild homology is that we'll take this complex and we'll evaluate its nth homology. Simple enough. A very nice homological algebra exercise says that you're actually computing Tor groups. So you can consider A as a module over a tensor A. And then this is the nth Tor group that's indicated in this line here. And since we're computing these Tor groups, one nice way to think about this construction is as some sort of derived version of this tensor product. So I could be putting a little L right here, and that's another way to model or think about Hochschild homology. Of course, thinking about that geometrically, we're then thinking of the derived self-intersection of A with itself. So that's kind of what this classical construction is doing. And people care about it for a good reason. So a classical theorem, the Hochschild-Rosenberg theorem, says that under certain hypotheses, Hochschild homology recovers the de Rham complex. So what are those? We'll assume that K has characteristic 0 and that A is a smooth finite type K algebra. In that case, the Hochschild homology in degree n is the nth piece of the de Rham complex. Here, omega is the object that co-represents K-linear derivations on A. And then to get the nth piece, we take the nth exterior power. And this has a very natural exterior derivative differential on it. And of course, if you wanted to do de Rham cohomology, you would take the homology of that complex. It leads to a natural question, which is, well, if this construction recovers the de Rham complex, is there a natural differential on the Hochschild homology that's compatible with the one on the de Rham complex? And here, the circle action comes in and allows us to see that. So I'll sketch that construction briefly. So what do? We've got this Hochschild complex, which I'll start denoting HH of A over K. And this is this derived tensor power of A with itself over A tensor A. And we might remember that these complexes by Dold-Kahn are the geometric realization of some simplicial commutative K algebra. So here is some notation for simplicial commutative K algebra. So this is a pre-sheaf category on the simplex category going into commutative K algebras. We can build this nice little kind of push-out looking diagram where we have picking out each copy on either leg. And it turns out by computation that this Hochschild complex is the geometric realization of the co-limit of this diagram. Well, what is that co-limit? It turns out that this is the geometric realization of S1 tensor A. So here we're using that commutative K algebras are tensored in, or simplicial commutative K algebras are tensored in simplicial sets. And we can realize the circle by just taking a little interval, looking at each of its endpoints, and in this diagram, gluing those endpoints together in order to get a circle. Okay, so here's this nice copy of S1 showing up. And that means that this Hochschild complex, more or less, carries an action of the circle. And when we push that through the Dold-Kahn correspondence, we get an action of the cochains on S1 on this complex. Well, we all know the homology of the circle quite well. It's this nice algebra here where the degree of epsilon is 1 and epsilon squares to 0. So what that tells us then is that we can act on these Hochschild homology groups by just multiplying by epsilon. And that is the so-called Kahn differential, which under the hypotheses of Hochschild-Rosenberg recovers the de Rham differential. So this is all extremely classical. And folks have used it for various purposes. This is Hochschild homology, to me at least, feels like a kind of chameleon. No matter which scenario you put it in, it seems to have something to say about what's going on. one place where we can start to mimic, maybe just a few more words there. I mean, so people use this with non-commutative algebras, and they start thinking about non-commutative geometry that way. People use this in other contexts, work of Schulze and Niklaus, to think about crystalline cohomology. Lots of places where this shows up. What we want to do right now is pass to a deeper base. So certainly a maneuver that many in the audience will be familiar with. Instead of working over a field, or maybe the integers, if we wanted to be more arithmetic, we can go down to the sphere spectrum. So just like we have tensor restriction adjunctions between Z modules, real vector spaces, complex vector spaces, we can also think of the category of spectra as somehow deeper inside of the derived category of abelian groups. So of course, to turn one of these into a spectrum, we take the associated Eilenberg-Mac Lane spectrum. So what happens when we do that with the Hochschild construction? What we can do is define, this is what Hochschild did, given a commutative ring object in the derived category of abelian groups, we can simply define THH to be this smash product of the Eilenberg-Mac Lane spectrum associated with itself over the smash product of HA with itself. And under the hypothesis that we're starting with a commutative ring object, this is the same thing as S1 tensor HA, where we're using here that spectra are also tensored in simplicial sense. So this is some spectrum. And if we take its homotopy groups, then we have the nth THH, or topological Hochschild homology of A. Now, in certain cases, this gives us nothing new, and I'd like to view that as a good thing. We're recovering the classical construction. It's a consequence of Serre finiteness that when A here is characteristic 0, this topological Hochschild homology just is the good old Hochschild homology of if we started with, say, a standard commutative ring. Of course, in other scenarios, it's different. The primary application is in characteristic P, and this allows us to do de Rham theory in characteristic P. So it's a deep theorem of Hesselholt, elaborated by others, that if we're working over a perfect field of characteristic P positive, and R is a smooth K algebra, then the nth THH of R decomposes as a direct sum of these particular pieces of the de Rham complex. That's an isomorphism of R modules. And this leads to p-adic Hodge theory and other contemporary work of Bott, Morrow, and Schulze. The other big use of THH that many at this seminar will be familiar with are trace methods. So using this as a sort of computational tool in algebraic K-theory. So Hochschild lifted the Dennis trace for Hochschild homology to topological Hochschild homology. And this factors through what's called topological cyclic homology. I won't have time to review the definition here today. The important thing is that this is something you could produce from THH just using the circle action. And a theorem of Dundas and McCarthy says that this cyclotomic trace is an extremely good approximation of algebraic K-theory, in more formal terms, an infinitesimal p-adic equivalence. So THH has had a good run. It's doing great stuff. It continues to be of interest. And it's also computable. So early work of Hochschild in the subject, despite having technical hurdles, he didn't have a nice category of spectra to work in. He was still able to, in terms of the tools available at the time, compute THH, and using that this is a smash product of HA with itself, we know that we have a Tor spectral sequence that computes the homotopy groups of the smash product. So here you have an E2 page, which is in terms of Tor over the homotopy groups of HA smashed with itself. And then the coefficients, maybe I could write pi star HA there, but that's just A in degree 0. And so we have this E2 term converging to the THH of A. And here I've gone and written out the numerics of the differential. And if you've got a ring A where you know these coefficients, you at least have a fighting chance of computing the spectral sequence. I'm going to focus on A, the field with 2 elements. And in that case, we know this object well. It's the dual Steenrod algebra, whose is a polynomial algebra on the Milnor elements Xi. So that's great. That's very explicit. And moreover, we know how to take Tor over a polynomial algebra. Another homological algebra exercise says that Tor is then an exterior algebra on these generators mu I that have the same T degree as Xi, but have homological degree 1. So I'm going to draw a picture of this now. Here we go. Remember that E2 page is this exterior algebra. And here I'm labeling each of these classes here with a sequence of integers. That's the corresponding product of mu i's. So for instance, this 1, 2, 3 here is supposed to indicate mu1 times mu2 times mu3. And similarly for the other classes. Of course, it's exterior, so we're never going to have a duplicated index. And what can we observe? Well, there's a single class in each even degree. And if you work out the numerics of the differentials, they all go 1 left and then down some amount. So just for grading reasons, we immediately know that this spectral sequence collapses and E2 is equal to E infinity. Now, something a little deeper that I won't outline here is that using a power operations argument, you can actually show that when you take the square of mu I, you actually recover mu I plus 1. So that's a hidden extension in the spectral sequence. And that then tells us that the THH of FP, the same story works out with different gradings for P not 2. We end up with FP adjoin mu, where mu is a generator in degree 2. So keep this in mind. When I get to the Motivic variant, which is coming soon, you will see similar patterns and similar, but far more elaborate computations come into play. This is a good time to pause before I jump into the Motivic story. If there are any questions, either in the chat or in the room, please feel free. All right, I've called your bluff and managed to get some coffee as everyone sits there. Okay, I can't see if there's a microphone moving around. No, okay. So let's get into the new stuff then. This is a K-theory and Motivic cohomology and homotopy seminar. So let's get into this familiar setting, or familiar for many. The idea is that we're just going to go from spectra to Motivic spectra and replace those Eilenberg-Mac Lane spectra with Motivic Eilenberg-Mac Lane spectra, the spectrum representing Suslin-Voevodsky Motivic homology. So many will recall Morel-Voevodsky's construction of the Motivic homotopy category. Just to be concrete here, I'll gloss it. We start with simplicial presheaves on the category of smooth finite type schemes over a field K. And then we need to remember certain colimits, which is what the Nisnevich localization does. And then we need to A1 localize, which inverts the affine line. So that gives us motivic spaces. And then thinking in terms of either dualizability or Thom isomorphisms, you see that for a stable story, you need to invert smashing with P1, and that leads us to the category of motivic spectra. Of course, in motivic spectra, that projective line actually splits into two pieces, its simplicial piece and its geometric piece. You can see that from the classical push-out description of the projective line as two copies of A1 glued along their common intersection. Since A1 is contractible, we realize that P1 is the suspension of A1 minus the origin up to motivic homotopy. And in this talk, I'll use the sort of algebrogeometric grading here, where we have this Mn graded sphere as m minus n copies of the circle and n copies of A1 minus the origin. So we get these bigraded homotopy groups where we map SMN into a motivic spectrum X. Well, if X is cellular or some other technical conditions, that might be enough to detect weak equivalences. But of course, in general, we'd have to pass to homotopy sheaves to detect those weak equivalences. But that sets our grading. Everyone here is familiar with the many wonderful inhabitants of this category, whether it's motivic homology, algebraic K-theory, Hermitian K-theory, or algebraic cobordism. Of course, I should probably add to this list the motivic sphere spectrum. At this point, we're really ready to define the Motivic Hochschild homology of a commutative ring, and it completely mimics the formula for THH just happening in this new category. And since this Eilenberg-Mac Lane spectrum is E infinity, we can also describe that as S1 tensor MA, where again, we're using the fact that motivic cohomology is tensored in simplicial sets. Here, I will just put a little daydream in the side here. Motivic spectra, of course, are tensored in much more than simplicial sets. Motivic spectra are tensored in motivic spaces. So in particular, we can ask, is there some more geometric version of Hochschild homology where we tensor with, say, GM instead of, which is A1 minus the origin, instead of the circle? That's not something that we explore in the present paper and work, but I think it's an interesting thing to consider. Okay, so we have this definition here, which is what we're working with. And when I write this double star, I'll just be talking about all of the coefficients taken at once. We're going to compute this. I wrote over C here. This is really over any algebraically closed field of characteristic different from P, where we're working with FP. And this is the theorem statement. So there's plenty to unpack here. Let's also remember that when we did the same thing for THH, it wasn't quite so complicated, right? That one just gave us FP adjoin mu, just that polynomial algebra. So here, there's a lot more going on. Let's begin to unpack it. So again, it's an FP algebra. We have a class tau, which is the thing that shows up in Motivic homotopy frequently in degree 0, -1. We have these classes mu I. Those are very related to this mu and the mu i's that showed up in the exterior algebra for the THH computation. And then we have these very fascinating XSF classes. So these are going to be tau power torsion in general, so a very new phenomenon. And there's a lot of them. So the indexing here says that we've got some indo function of the natural numbers, that's f. We'll assume that it has finite support. I can write that in here. So almost everywhere it's equal to 0. And then we'll take some subset of the support. And we're going to have a generator for each pair S comma F of that form. So an awful lot of them. And then there are relations, which are written down here. So the first one says, let's think of the case where P equals 2. In THH, we saw that mu I squared was mu I plus 1. Here we see that mu I squared is tau times mu I plus 1. So that relation gets twisted by the class tau. We see that all of these X classes that there are so many of, every single one of those is tau to the P-1 torsion. And then finally, there are some relations amongst the X classes. And this is a gnarly formula. It says that when we multiply two of them, it's equal to some sum of some coefficients times some other X classes. It'll turn out that most of these coefficients are 0. I didn't have space on this slide to include the definition of epsilon u. That's here, so I just shrunk what we were looking at. And here is the definition of epsilon u. So we have this kind of wild product of binomial coefficients, and then we define epsilon u in terms of some sum of those products of binomial coefficients. So this, I don't know a precedent for any computation that looks like this. This is kind of a wild and woolly way to capture the Bochstein homomorphism applied to a divided powers algebra that will show up in just a bit. But it's one way to present that, and it allows us to just get this clean-ish statement of the final answer. It is explicit, at least. Okay, so where are we headed from here? I've got 2 goals for the rest of the talk. I want to give you an idea of how this computation comes about when P is equal to 2. And then I want to get to some of those further directions, what this tells us about the Motivic homotopy category and what questions it inspires us to ask. So let's get into the nitty-gritty here. Let's try to compute. So here's the strategy. Because the spectra that we're dealing with are cellular, which is a consequence of the Hopkins-Morel-Hoywa theorem on HF2 being a quotient of algebraic cobordism, or MF2, sorry. We are allowed to run various TOR spectral sequences, universal coefficient spectral sequences. And so we'll use those. And the input, just like the topological case, is again going to be the dual Steenrod algebra, but here in the Motivic setting. So let's recall that the coefficients are F2 adjoint tau. Again, we're over in algebraically closed field, so no Milnor K-theory contribution outside of degree 0. And tau has degree 0 -1. This dual Steenrod algebra, it has the CIs like the topological one, But we also have tau i's and tau. So these are like you see in the odd primary dual Steenrod algebra. And when we take the square of tau I, we get tau times xi plus 1. I've written down the explicit gradings here. So we've got more to work with in the Motivic setting. And then we'll use what's become a relatively common computation strategy. We'll try to look at the tau inverted and the mod tau pieces separately. So when we do tau inverted, recent work of Thom Bachmann and Paul Arne O, and I might be omitting a collaborator, which I apologize for, identifies that with Ital motivic theory, so where you do the Ital localization instead of Misnevich localization. We will compute that after inverting tau in these coefficients, we get the old picture, THH, adjoin positive and negative powers of tau. Okay, so that's kind of clean and nice, and maybe even what you would expect, thinking in terms of Betty realization. What's challenging and interesting is that when we go mod tau, we get a lot more. So we have a divided powers algebra on these classes called mu I bar, and we have an exterior algebra on these lambda I bars. Step 3, I'm going to go into these steps in more detail. Steps 3 through 5, I'll mention here, but not go into detail in the talk. We show that the tau torsion piece there, that divided powers tensor exterior piece, it accepts the tau torsion in here as an injective image. And that image is exactly that of the tau Bachstein. And then that crazy presentation in terms of the x's, that is then the presentation that we give for that tau torsion. Finally, combining the tau and tau torsion pieces in a pullback square gives the final answer that was in the theorem statement. I would, there's some challenging bookkeeping in this process, but I would call these steps bookkeeping. And in some sense, this is kind of the core of what's going on in the computation. Okay, so let's do the Ital piece where tau is inverted. So we're talking about inverting tau everywhere, and that means that we can run this Tor spectral sequence where tau has been inverted everywhere. When we invert tau in the Motivic dual Steenrod algebra, well, over here, we've got this relation, tau I squared is equal to tau times xi plus 1. Well, now that tau is invertible, we see that the xi i's are redundant. We can solve for them. And so we can represent this algebra as just polynomial on the taus, along with this tau plus or minus 1. Okay, that tells us then that the Tor spectral sequence, it's now trigraded. It has the homological degree and the 2 internal motivic degrees. It's over this algebra that we just derived. And the coefficients are just Laurent polynomials in tau. Another nice homological algebra exercise says that this is then an exterior algebra. So it's basically looking like Tor over a polynomial algebra. And that spectral sequence will converge to the tau inverted Motivic Hochschild homology. And quite similarly to the topological case, degree considerations will give us collapse of this spectral sequence. And a little deeper, a similar power operations argument will tell us that mu I squared is tau times mu I plus 1. Okay, and that gives us the computation because, well, we just said that this is polynomial along with this relation, but tau is invertible, so we can solve for all of the higher mu i's, or just have a polynomial algebra on mu0 adjoin this Laurent generator tau. And I've drawn a picture here. It's not a picture of this, right? This is the picture before tau is inverted. So what I'm trying to indicate here is, well, if you look at the Motivic Hochschild homology and look at its image inside of Motivic Hochschild homology with tau inverted, this picture is what you'll get. So here, these downward lines are powers of tau multiplication. And the mu i's, right, we can read this off, right? Mu0 squared lands here. And this relation is telling us that tau times mu1 is equal to mu0 squared. Similarly, mu2 squared, that lands here, is tau times mu3. And that's the kind of interesting pattern of tau divisibility that we know we see in Motivic Hochschild homology. Let's now go to the mod tau story. So here we're going to talk about quotienting by tau. And if you remember the relations that we had in the dual motivic Steenrod algebra, they said that tau I squared was equal to tau times xi plus 1. Well, if tau is now 0, that tells us that the tau i's are all exterior. And so this is the ring over which we'll be computing Tor. The coefficients mod tau are just F2. And so we're taking Tor over this polynomial tensor exterior business of F2. And the polynomial will once again turn into exterior. And if you've played these sorts of homological games before, you won't be surprised to see that the exterior turns into this divided powers algebra. So this is our E2 term, and it will converge to the mod tau, Motivic Hochschild homology. There's more work now. I don't have a good way to present this without just doing a lot of arithmetic in front of you, so I'll send you to the paper. Basically doing some advanced degree yoga, you can still check that there's no room for differentials. And furthermore, in this case, there's also no hidden extensions. So once you've checked that arithmetic and sort of combinatorics of where things lie in this trigraded spectral sequence, you deduce that E2 is equal to E infinity, and that is the mod tau coefficients of MHH. So here we just have exterior, tensor, divided powers. So as I indicated earlier, this is somehow the meat of the computation. We can now stitch these together in a pullback square. We could have stopped with that statement, but then there's some fancy bookkeeping in order to give a nice presentation of that pullback in terms of these Indo functions of the natural numbers. So do go take a look here if you're interested in how that portion works. Okay, and now I want to talk a little bit about the consequences, and I hope you all will have questions and ideas about this as well. Straight off the bat, we see classically that THH of FP, it's an HFP module, right? And we know its groups, so we immediately get a splitting of THH-FP. It's just a bunch of suspensions of the Eilenberg-Mac Lane spectrum. In the case of Motivic Hochschild homology, something wildly different happens, right? We have all of those X classes. Each one of those is tau torsion. So in particular, we know that MHH is not a free MFP module. So we were surprised to see that. And you can push this. You can start thinking about what has to be different in the motivic world in order for a statement like this to be true motivically. Well, here are the things that are true in spectra that more or less lead to this observation. First off, Mohoald showed that the F2 Eilenberg-Mac Lane spectrum is a Thom spectrum. Thom spectrum, in fact, of an E2 map whose target is loops 2 S3. So that's interesting. And then work of Andrew Bloomberg and others shows that in very general scenarios, THH of a Thom spectrum, under a little hypothesis on the topological Hopf map, is actually a Thom spectrum, which is in terms of the first Thom spectrum smashed with something involving the base of the first bundle. And then finally, we have James splitting, which says that stably, if we take the classifying space of loops 2 S3, we get a wedge of spheres. So how does this lead to a statement like the classical one? Well, if we know that this is a Thom spectrum, then we know THH of it is some Thom spectrum smash B of the base, and B of the base splits as a bunch of spheres. So that then takes us back to this statement. At least one of those things has to not work motivically. So what'll it be? We could have that it's not the case that MF2 is a Thom spectrum. Now here I've chosen a particular base, a base that's inspired by work of Mark Behrens and collaborators that shows that this is true C2 equivariantly. Okay, what else could go wrong? It could be the case that we don't have this splitting for MHH of Thom spectra. I think this is the statement that's most likely to be true. So my guess is that either MF2 is not a Thom spectrum, or we do not have a GM James splitting. So if this were true, then, and 2 were true, then we'd be computing MHH of MF2 as MF2 smash this object. Well, a motivic analog of James splitting would say that, you know, maybe this does split as a wedge of spheres. Maybe that's false. So probably 1 is false, or 3 is false, or both of them are false. That's my best guess. I did, what we have proven is that at most 2 of them are true. So I think these are interesting questions to look into. I did turn to social media and ask them to solve this problem, and they were split as well between the 2 options that I just outlined. But that's where this project is presently. I think it's a neat and novel computation. I think there are obvious follow-on questions in terms of this type of stuff, and also computing MHH over other base fields, thinking about you know, things like a Dundas trace map in the motivic setting, and also thinking about tensoring with other motivic spaces. So lots of directions to go from here, and I certainly welcome your questions. Thank you.
Thanks, Kyle. So can you hear me, Kyle?
I can hear you, yes.
Okay, could you hear the applause? They liked your talk very much. I'm going to ask if anybody has any questions. Hold on, wait.
A lot of your talk was in purple and I couldn't read the purple. So could you give the definition of MHH again?
Absolutely, yes. So I will share my screen here again and write that out. There we go. Okay, so yeah, I apologize about the purple there, didn't realize. But MHH of commutative ring A is the Motivic Eilenberg-Mac Lane spectrum of A smash over NA smash MA with MA. This is a specialization to the case of a commutative ring for a general A infinity motivic spectrum. We could say that MHH of what's a good letter? Let's call that E, is E smash over E smash E with E. So here we're kind of conflating A and MA. It's worth noting that this is in the E infinity case, that both of these are S1 tensor, the object in question.
Okay, thanks. Any other questions?
So I saw that most of your results follow from a decomposition along tau invertible and mod tau or tau torsion information. Can this be done on the level of categories using this result from Strigowski, where he decomposes P-complete cellular motivic spectra over C into purely topological information?
Yeah, okay, so this is a wonderful question, and it is something I've thought about. I have not particularly made progress here. So I'll rephrase this as just, is there I was going to write Strigowskian, but I don't think I can spell that. So let's say a synthetic interpretation of these results. I'd love to know the answer. I think the mod tau part is especially interesting. So mod tau in the synthetic homotopy category, you're working with this stable cohomodule category for mu star mu, the complex cobordism spectrum, or even comodules. One way to interpret our results is to say that we have done a computation in that setting. We know this Hochschild homology style object in this stable comodule category, and we can write it down explicitly. I think the obvious question is whether there's some kind of synthetic spectrum that we can identify that computation with that has a more conceptual meaning, something we can understand that way. So yeah, I'd love to know the answer, and if you have any ideas, let me know.
Some other questions? Hold on. Sending you over to Tom Bachmann here.
Thank you. Hi, Carl. Just a comment, which is that, I mean, there's also a notion of norm spectra, and the functor from norm, the forgetful functor from norm spectra to E infinity rings, it commutes with tensoring by S1. But I suspect that it won't commute with tensoring by GM. So maybe if you get into the GM thing, you also want to look at the normed analog.
Awesome, thanks. I'll keep that in mind.
Some other questions? Oh, you had your chance. Wait, we'll get you next. So here you go. Say who you are.
Oh, hey, Kyle, this is Thomas Brazelton. I was curious if you take Betty realization, if you're working in like the real motivic category, do you get mapped to some like C2 equivariant version of THH, or do you know sort of what it corresponds to there?
Yeah, so the question here is what happens over the real numbers if you take some kind of C2 equivariant Betty realization of one of these gadgets. Pretty sure that commutes with the tensoring and simplicial sets. So I do think you'd recover. I'll put a little question mark here because I'm terrible on the fly. But yeah, probably you do get something like the THH of the Betty realization. And in the case of the motivic Eilenberg-Mac Lane spectrum, that would be the a particular equivariant cohomology spectrum. So yeah, I think there are things to look at there.
So there's another question here.
Sorry, just as a follow-up to this tau picture, could you elaborate on the computation of the tau inverted Motivic Hochschild homology groups? Like, is this tau inversion functor, like, does it have some nice description?
Yeah, well, so it has a great, it has at least two wonderful descriptions. So let's be super concrete and work over the complex numbers and invert tau. Then we're basically dealing with the non-equivariant Betty realization of the Motivic spectrum we started with. And so that is going to be just THH. So over C, you don't really need to do the computation. You could just rely on the Betty realization and some theoretical results about inverting tau. Inverting tau is also this sort of generic fiber situation in synthetic homotopy. And again, you're going to recover the classical THH. So the reason we go through this whole Tor spectral sequence is in order to do this in positive characteristic as well. And there, maybe someone knows how to do that in a more conceptual fashion, but it's also, well, these are fun computations. I mean, you ought to do them.
Okay, I have a quick question. You have a S1 sitting there. Do you have a cyclic homology version?
It's there for the investigation. Yeah, we haven't gotten that far yet. I think it's mostly formal to push through those constructions and then start asking questions. For me, you know, I'd want to construct some kind of Dennis trace before I went to the trouble of looking at the cyclic homology. But yeah, I'd love to see where that thread leads.
Some other questions? Okay, I think you've questioned us all out. Thanks very much for your talk, Kyle, and thanks again.
Okay, thanks everyone, and do please reach out if you have any questions or comments.
Thanks. Take care. Bye-bye.